a lot this semester. We're just going to talk about some more specific properties of them in this chapter. So to remind you, solution is just another word for a homogeneous mixture where the two things are evenly dispersed in each other. We usually talk about solutions as being dispersed down to the atomic or molecular level, so like individual molecules separated from each other. That's not always the case, but we do want to be specific that when we talk about solutions, we're talking about all different types of these mixtures, not just like something dissolved in water, which is kind of the classic solution, salt dissolved in water. That is a solution for sure. There's lots of other kinds too. So let's take a look at this chart from the book and look at some of these other types of solutions that can exist. We'll look at some of these terms too. So our typical, when we think of a solution, we think of something usually like this one down here, seawater, which we can think of as a solution of sodium chloride or salt in water. In that case, we have two parts of the solution that we are usually going to be talking about, the solute and the solvent. The solute is the thing that is dissolving in the solvent. The solvent is the thing that there's more of. As we can see from this chart, or as we go through the chart, that definition is not necessarily always useful because really it's just that there's less of one and more of the other. Because there's lots of different ways to have solutions. So for instance, a gas in a gas is a solution. You could say that air is oxygen dissolved in nitrogen. You could say air is oxygen, carbon dioxide, and water dissolved in nitrogen, whatever. You could say that it's these things dissolved in this whatever there's more of. So that would be a gas solution. We can have three different types of liquid solutions. You can dissolve gas in a liquid. Carbon dioxide, for instance, can dissolve in water. That's what we call carbonated water or soda water. You can dissolve HCl. HCl is a gas, hydrogen chloride. But when you dissolve it in water, you get hydrochloric acid, which is the gas actually dissolved into the water. Then you can have a liquid dissolved in another liquid. So we saw this the other day in lab. Vinegar is acetic acid dissolved in water. So that's another type of a solution. In that case, the solute is liquid and the solvent is liquid. So both liquids. And then the ones we talked about, the kind of classic solution that we always think of is a solid dissolved in water, which could be this style. And then you can actually have a solid solution as well, where you have a solid dissolved in another solid. In order to make that solution, you usually have to melt them first, but then you can allow them to cool and freeze. And something like brass is zinc dissolved in copper, because there's less zinc, there's more copper. So there's different ways of defining solutions, but in each case, we can identify a solute, the thing that there's less of, and a solvent, which is the thing that there's more of. All right. So let's look at why solutions form and what it means to have a solution. And we're going to use that example of salt and water. So if you want to make a solution of salt and water, you take some solid sodium chloride and you add it to liquid water. Let's make a diagram of what that looks like at the molecular level. So if we really zoom in on this stuff, what does it look like? So what does sodium chloride look like at the molecular level? If you zoomed into the individual, looking at the individual ions and inside there, what would it look like? How could you describe it? What's it made up of? Well, the sodium chloride part, what's that made up of? Sodium ions, chloride ions, right? So how are they in relation to each other? What are they doing in the solid sodium chloride? They're together. Yep. Yep. This is not hard questions. Just, they're just together. They're there. They're together. You don't have to say anything fancier than that. So we could draw that because we've got positive sodium ions, negative chloride ions, and they're not connected in the way that they're like sharing electrons because they're not covalently bound, but they are close together. Right? They are stuck together. So maybe we would show sodium like this. We would show chloride like that. It's sodium, chloride. And they kind of keep alternating like that through the structure. Packed together tightly, negative and positive ions attracting each other. So that's sodium chloride, these strong ionic forces connecting them together. Okay, what does water look like? What does liquid water look like on that same scale, that atomic scale? What does it look like? So you got water molecules, right? What are they doing with each other? Kind of.
They're closer together, but not like
They're close together. Not stuck like that, that's true. How are they stuck together? I mean, they have to kind of be stuck in some way because otherwise they would be gas. The fact that it's a liquid tells you there's something there. So what's going on with those? Remember what it's called? How do water molecules interact with each other? What's it called when they interact with each other? I've got some studying to do for this exam coming up next week. Yeah. It's called hydrogen bonding. So they're connected through these intermolecular forces called hydrogen bonding. And we can draw that. So you've got your water molecule, which has a positive side and a negative side. We always said the positive side is the hydrogen. The oxygen has the negative because it's more electronegative. And then those connect with other water molecules through this hydrogen bonding interaction, which we said is not as strong as an actual covalent bond. They're not sharing electrons. And it's also not as strong as an ionic interaction. It's not like the sodium and chloride because it's just these partial charges. But they're still attracting each other. They're still connected together in this way. I'm going to draw that as much as we want. It's being weird again today, so it's not quite working well. But something like that. So you've got two separate pure compounds whose parts are attracting each other. If we want to make a solution, we have to put these things together. And at first, that seems like maybe not a great idea because all these things are pretty happy on their own. They're well connected on their own. So in order to make a solution of sodium chloride and water, we have to break up both of these networks and kind of intermingle them and put those sodiums and chlorides in between the water molecules. So let's draw what that might look like. What happens is you take a sodium ion, which is positively charged, and the water molecules surround that sodium ion, and they surround it so that the negative parts of the water molecules are pointing at or interacting with that sodium ion. We know the oxygen has the more negative part of that molecule, is the more negative part of the molecule. So you expect to see that kind of an arrangement. And we draw it as around like this because we only have 2 dimensions on our paper. But in reality, that would be a sphere. You have water molecules completely encapsulating that, that sodium ion. All right. So then, since there's way more water in the solution, what you would expect to see is the extension of the hydrogen bonding network as it goes on and on throughout the solution. So those water molecules are going to be in the network of other ones, and they've sort of brought the sodium ion in by encapsulating them in this sphere, which is called a solvation sphere. So we'd say those ions are hydrated, they're surrounded by water, and they're brought into this water network. The chloride ions are going to do the same thing, but to the other side of the water molecule. So our chloride ions over here are going to be more pointing at the hydrogen side, or the hydrogen side of the water molecule is going to be pointing at the chloride ion instead of the oxygen side. And so now we kind of have a picture of what it might look like inside that solution. We have ions that have been separated from each other, surrounded by water molecules. In order for a solution to happen, this has to be energetically better than the previous situation. So there has to be a reason for these things to rearrange in this way. And part of that reason is something called entropy, which has to do with the disorder of the system. And part of it is our regular energy type things, where we say, what is the energy of this interaction? What is the energy of that interaction? When you have so many water molecules surrounding and having interactions with these ions, you end up having an overall stability in energy, when we talk about energy, with respect to the original situations. So even though originally the sodium and chloride were stuck very well together, and the water were stuck very well together, in the solution, they're actually all stuck even better together. So that's one of the reasons that can form, and one of the reasons that a molecule like water can dissolve an ionic substance like sodium chloride, because it can make these interactions with the ions, because again, it's polar. So let's revisit these terms. Polar and nonpolar, which we looked at back when we looked at electronegativity and all that. Things that are polar are able to make these kinds of interactions with ions and with each other. Things that are nonpolar are not. So if we take a nonpolar solvent like hexane, which is just made of carbon and hydrogen, this can't happen in that kind of a solvent. So salt is never going to dissolve in hexane. The hexane and salt make together are essentially nothing. There's no polarity to hexane. There's no positive and negative side that can interact with the ions. So hexane's going to stay with itself, salt's going to stay with itself, the sodium and the chloride, and they're not going to mix. And so a lot of what we talk about with solubility is thinking about these ideas. What are the interactions in the material together? And then what are the interactions between the two materials? In lab today, we're going to look at some solubilities of some different materials and some different solvents and see how that works. So if we have a more polar situation like this, we would expect a polar solvent to do a better job at that. If we have a non-polar molecule, we expect a non-polar solvent to do better. So let's look at an example of that. Let's take iodine molecule. Iodine molecule looks like this. It has no polarity. There's no negative side, there's no positive side. It's all even. So iodine molecules stick together by something called dispersion forces, if you remember that. Those nonpolar forces that allow nonpolar molecules to stick together. So we would not expect for iodine to make the same kind of interactions with water because it doesn't have that same polarity. Instead, we would expect it to dissolve in a nonpolar solvent like hexane, which is this big molecule that has a bunch of carbon and hydrogen. If we, you may not remember, but if you look up carbon and hydrogen on the electronegativity table, you'll find that they're pretty close to the same. And so this is nonpolar. These are both nonpolar. So those can interact with each other because they have the same types of intermolecular forces. Iodine's a solid, hexane is a liquid, and so the iodine can dissolve into the liquid. That's going to look kind of the same. You don't have to copy this down, but I'm just going to make a bunch of these to kind of show what that would look like. So remember that with dispersion forces, it's not about positive and negative. It's just about all these things kind of lining up together. Like that, and they all kind of attract each other, even though there's no positive and negative. So water doesn't fit well in there because it's positive. It has a positive and negative side. It's polar. But a nonpolar thing like iodine could. Well, let me do it in a different color here. So iodine could easily kind of sit within these molecules wherever it wants because it has the same types of intermolecular forces. So solubility is described by or is predicted by the similarity or differences of the intermolecular forces. Molecules with similar forces can go together. Molecules with different forces can't. So you've got the polar and the ionic stuff together, and then you've got the nonpolar stuff together. So one of the things we're going to do in lab is look at some examples of that and try to predict whether these things will dissolve or not, and then test it out and see. All right. This was something that we looked at a couple of weeks ago, electrolytes. We did that light bulb experiment in lab. Remember that, where we put the different solutions in? Sometimes the light bulb lit up, sometimes it didn't. And that had to do with something that we called an electrolyte, whether it was strong electrolyte, weak electrolyte, or non-electrolyte. Well, now we can also think about what that means for the solution. So a strong electrolyte is a substance that breaks into ions in solution. So we could say it breaks up into ions completely. When you dissolve sodium chloride in water, you get a complete separation into the two aqueous ions. So you get sodium ions, you get chloride ions. You don't have any sodium chloride compound left over in that solution. It's just ions in solution. And so we call that a strong electrolyte. That's what happened with some of those acids too. And this will be important terminology when we go into the next chapter, which is acids and bases, and we start talking about whether or not we have a strong or a weak acid. That has nothing to do with like how corrosive it is or how dangerous it is. It has to do with whether or not that acid breaks apart into ions in solution or not. And so that's where this term strong comes from. A strong electrolyte makes lots of ions in solution. A solution made from a strong electrolyte will conduct electricity because it has lots of charged particles in there that can help move the electrons around and conduct the electricity. Then you've got a weak electrolyte, which has some ions, but mostly neutral molecules or compounds. We saw that with the acetic acid, the vinegar solution. it made some ions. It did conduct some electricity, just a little bit. Just like, remember the light bulb was like really dim when we tried that one? And that showed that there were some ions in solution, but most of what was in there was still whole molecules, whole neutral molecules. So that's the weak electrolyte. And then finally, we have a non-electrolyte, which is all neutral molecules and no ions. So that would be something like glucose. That's solid glucose, like sugar. You can put that in water, and it dissolves, right? You can dissolve sugar in water. But it doesn't change what it is. It doesn't become ions. It doesn't break apart. It just becomes solvated. So it gets surrounded with water, becomes in a solution, but still is the same thing. It doesn't break apart and form any ions. So that's a non-electrolyte. This is going to become important when we talk on Thursday about osmosis and osmotic pressure, because things that form ions actually form more particles in solution than they start with. When you dissolve sodium chloride in water, like if you dissolve 1 mole of sodium chloride, you get a mole of sodium ions and a mole of chloride ions. So you actually have 2 total moles of ions in solution in that case, and that has effects for like how it interacts with the blood cells and things like that. We'll get into that on Thursday. But thinking about whether or not something makes ions when it goes into solution can affect how it's going to behave in solution as well. Okay, so there's some of those definitions. Now let's look at the thing that we're going to do mostly in lab, spend most of our time doing in lab today, which is the solubility. You all right? You have a question?
No. I did the wrong pre-lab questions.
Oh, which pre-lab questions did you do?
9. Because when you said that we're learning about that next week, I was like, wait, that's what I did.
You got to get like an hour. You don't have to listen to me. I'm not saying anything important. Just do the. No, it's fine. A lot of people have done that, right? I know at least a few other people have done the wrong pre-lab. So if you do that, if that ever happens, I'll just give you credit for the pre-lab that you did, and then because you did one, and then you can just have it ready for the next week. All right. So anyway, I know it happens. Solubility. We're going to be measuring some solubilities in lab, and this is a measure of how much solute you can dissolve in a given amount of solvent. So solubility is how much solute will dissolve in a given amount of solvent. So will 100 grams dissolve? Will 200 grams dissolve? How much? So it's usually given in a measure of grams of solute per some standard amount, like 100 grams of solvent. So like 10 grams of this solute will dissolve in 100 grams of water, something like that. So let's look at some solubilities and see what that looks like. I think, again, this is easiest if we look at this picture. 291. not that one. This one. Okay. All right, so here is a chart of the solubility, how much solute will dissolve in a given amount of solvent over, versus temperature. And so what you see is for all of these solutes that are listed, as the temperature increases, more of it will dissolve in the same amount of water. So what happens when you exceed the solubility? So for example, let's say we have a, let's say we're at 20 degrees C, and I'm just going to pick a nice number here. In 20 degrees C, let's say you have 140 grams of Ki, because this purple curve is Ki. So you got a solution at 20 degrees C. You dissolve 140 grams of Ki. That's the solubility. What happens if you put an extra 20 grams in? Like what will happen if you exceed that amount? Any ideas? Think about it this way. Does anybody like really sweet beverages? All right, so you're putting sugar in your drink. You keep putting sugar in, taste it, it's not sweet enough. Keep putting sugar in, taste it, not sweet enough. Keep putting sugar in, taste it, not sweet enough. I've also had this experience. Eventually what happens? It's too sweet, yeah. What happens to the sugar? Right, eventually it's not going to dissolve anymore. Once you get to a certain limit, all the more that you put in just kind of drops to the bottom. It doesn't dissolve. And that's what these lines are telling us. So if you're at 20 degrees and you put in 140 grams of Ki, everything's good. You put in 150 grams of Ki, that extra 10 grams is just going to fall to the bottom and not dissolve. So those lines tell you how much of that solute can you dissolve in 100 grams of water. And you can see that change over the temperature. So the higher you go for most solutes, the higher in temperature you go, the more you can dissolve. That's why, like, if you've ever tried to put sugar in iced tea versus in hot tea, it's a lot harder to get to dissolve in the cold beverage than in the hot beverage. Now that's, I should say, even though those are all going the same direction, it's not true for all solutes. Some solutes actually go the other direction, where there's less that you can dissolve as you heat it up. But for most of them, for most solid solutes, that's how it works. If you reach that point, you have what you call a saturated solution. If you have a saturated solution, no more solute can dissolve. So you're at that solubility point. You're at that point where nothing else can go in.
And how do you know what that point is?
That's a good question. So you have to measure, and that's what we're going to do in lab today. So you're going to look for that point at which some of the solid won't dissolve and just falls to the bottom. Once it falls to the bottom, you know you have more than what the solubility tells you you can have. So you have to measure it.
It's like no problem solving. It's just literally
right.
Physically
doing it, right.
A plus B and yeah.
Yeah. So the problem solving part of it is like, if you construct this graph, you can then find what that is from this graph. So let's look at an example of that. So here's how a question might be worded. At 20 degrees C, will 50 grams of glucose dissolve in 50 grams of water. So to solve a problem like that, first we have to recognize that this isn't just a straight up graph reading issue, because the graph tells us grams of solute per 100 grams of water, and we want to know if 50 grams of glucose will dissolve in 50 grams of water. So what we have to do is we look at 20 degrees and we see, okay, the solubility of glucose at 20 degrees is about, let's call that 75. I'm just estimating here. It's less than 80. 70 would be here, so maybe it's a little higher than that. So let's call it 70, 77. Okay. The solubility of glucose is, we'll say 77 grams glucose per 100 grams of water. And that's the number that we got from the graph. We went to 20 degrees, we looked up, and the glucose was about 77. So proportionally, we can figure out how much solvent, or how much that would work for 50 grams of water, right? Because 77 divided by 100 is 0.77. What we have is 50 grams of glucose in 50 grams of water, which is 1. So we have a higher ratio of glucose to water than the solubility. So no, 50 grams of glucose would not dissolve in 50 grams of water. The other way we can ask that question is, if 77 grams of glucose dissolves in 100 grams of water, which is what we get from the graph, how much would dissolve in 50 grams of water? So it would be proportional, so it would be half of that. So 38 and a half grams of glucose. So 50 grams is way too much. Yeah.
This is the real lines of what it really is?
Mm-hmm. Yep. There's the real lines of what the solubility is at different temperatures. Another thing we can ask about this, say, okay, well, you know what? Screw the graph. I want to dissolve 50 grams of glucose in 50 grams of water. How do I do it? What would I have to change to be able to dissolve 50 grams of glucose in 50 grams of water? The heat, yeah, we have to change the temperature. So at the point at which the grams of solute and the grams of water are equal, that would be 100 grams of solute per 100 grams of water. So that's right like here. So once I get to about, I don't know, 30 degrees, let's say, now I'd be able to dissolve those 50 grams of glucose in 50 grams of water. See how that works? So it's kind of interesting with these definitions of solute and solvent, because actually beyond that point, you really have more glucose than water. So it's really more like a water solute dissolved in a glucose solvent at that point. Has anybody ever made like syrup out of just glucose, sugar and water? It's sucrose because it's table sugar, so it's a little different, but it's the same idea, where you like mix sugar and water and you heat it up to like get it to dissolve. And you can make a syrup, a stable syrup, that has way more sugar than water, and that's what this shows at those higher temperatures. That's what you do when you make candy and that kind of thing. All right, so what we're going to do today in lab is we're going to look at different points on this curve for, I think we're going to do this one, potassium nitrate. Each group is going to have a different amount of solute, and you're going to heat it up and cool it down sequentially, like heat it, cool, and try to find that point at which it stops being soluble. And you'll see that because when it's soluble, it'll be totally clear, and then when it's insoluble, all of a sudden you'll see a bunch of little things floating around again. So you'll be able to find that point at which it's no longer soluble. All right. For the second part of lab today, we're going to be looking at a saturated solution of sodium chloride and figuring out how much sodium is actually in there. And one question I always get is, if we look at the samples in lab, the bottle of saturated sodium chloride always has a bunch of salt stuck in the bottom there. So why is that? If you wanted to make a saturated solution, why can't you just look at the graph and say, okay, it's 20 something degrees in here. I'm just gonna get that much glucose, 82 grams of glucose. I'm gonna dissolve it in 100 grams of water, and I've got a saturated solution. Why isn't that the best way to make a saturated solution? If we truly want a saturated solution, meaning we want a solution that has as much water or as much solute as possible in the water, why can't we just like measure out the solute and dissolve it in that much water? Ideas? It's because things change. Because temperature changes, right? If the temperature goes up a little bit because the air kicks off or the sun comes in the room or whatever, somebody walks by and farts, I don't know. It goes up a little bit and suddenly you don't have a saturated solution anymore because now you're higher on that curve. So it's no longer saturated. Similarly, if the solution absorbs some water from the air or if some water evaporated from the solution, you no longer have the exact same situation. So if you want to make sure you always have a saturated solution, there's actually an easy way to do it. Looks like this. You just simply leave a bunch of extra solute in the bottom of your container, in the bottom of your solution. So that way, there's always some dissolving, some recrystallizing back into the salt form. If you lose some water, everything else will adjust to compensate. If the temperature changes, everything else will adjust to compensate. So as long as there's a stock there in the bottom of the solid solute, the solution part, the liquid part, will always be saturated because it'll always be able to pull some more out of the extra part floating or sitting at the bottom if it needs to. So whenever you have a saturated solution in lab, like we're going to be working with today, there should be a bunch of salt sticking to the bottom or resting on the bottom of that solution. It's not supposed to be perfectly clear because that's how it allows it to compensate and make sure that it's always saturated. When you work with that in lab today, just make sure that when you pour it, you don't like shake it up, just leave that stuff on the bottom and pour gently, and all the solids should stay on the bottom when it's supposed to. So that's how you make a saturated solution. All right. So we talked about how most solid solutes increase their solubility with temperature. Gases actually do the opposite. Gases decrease their solubility with increasing temperature. And the best way to think about this is if you've ever had a carbonated beverage, does it go flat faster in the fridge or does it go flat faster when you leave it out in the sun? It's actually the sun. So that's not a good way to remember it. But no, yeah, as the drink warms up, the CO2 won't be as soluble, and so it'll escape faster. That's also why, like, if you have a carbonated drink in the fridge that's sealed, you take it out or you leave it in a hot car, like you can feel it getting really tight.
Yeah, but then more when you open it.
Right, because what's causing that? That's all the gas that's already escaped from the liquid and is stuck in that little spot at the top of the thing. So yeah, if it's warmer, there's more gas out of the solution than in it, and so you get that bigger fizz. So if you really want to if you ever carbonate your own drinks, if you want to really make sure you get as much carbonation as possible, you have to get them as cold as you possibly can without freezing them, and that's going to allow the most gas to dissolve in there.
So that's why it's like thicker too, right? Like it tastes like more sugar than anything.
No, I think that's just how it tastes. Like you're saying a warmer one tastes sugarier?
It tastes different.
That's more how your taste buds, and your nose understands taste. That when things are warmer, you're more sensitive to it, and when they're colder, you're less sensitive to it. So warm, that's why, yeah, so it definitely tastes different because your taste buds react to that differently, to different temperatures. All right, the last thing we're going to do today is talk a little bit about concentration. We're not going to get all the way through it because it's kind of a big topic, and we'll practice it more on Thursday, but we want to introduce it.
Is this all part of the same chapter?
Yeah, this is all part of chapter 9.
This won't be covered in the test.
Yes, it will be. All chapter 9 will be on the test. So concentration tells us how much solute is in a given amount of solvent or solution. Sorry. If we want to do that in a math way, that looks like this. Concentration is the amount of solute divided by the amount of solution. And I'm using these vague terms like amount because there are lots of different ways to say amount. And we're going to look at some of the different ones. Concentration is always a measure of those, is always that. But amount could mean grams, amount could mean milliliters, liters, moles. We're going to look at some of the different concentration measures that we get when we switch those units. But the ratio is always the same. It's always amount of solute divided by amount of solution. The only thing that changes is the units, the specific units for amount. So when we make a solution of something, we need to use concentration because we need to know how much is in there. Like if we want a certain amount of sodium chloride for our reaction, if we had solid sodium chloride, we just weigh it out and say, okay, we got 20 grams of sodium chloride for our reaction. But if we have a solution, it depends how concentrated that solution is. If there's a whole bunch of sodium chloride in there, that's going to mean we need less of that than if there were just a little bit of sodium chloride in there. So the concentration tells us how much is in there, so we can figure out how much we need to use for our reactions or whatever we're doing with it. Okay, so let's look at our first concentration measure, which is going to be kind of the easiest one or the most basic one, which is called mass percent. Mass percent is sometimes written as a percentage sign and then M over M, or M/M. And mass percent is just a simple ratio of the masses of each of the solute and the solvent. So mass percent equals the mass of the solute divided by the mass of the total solution. And it doesn't have to be grams either. It can be any measure of mass. So it can be kilograms, it can be pounds. The units actually cancel in this measurement. So you end up with a percentage that doesn't have any units. So because of that, we'll also usually multiply this by 100% to make it into a percentage. So let's look at an example of what a mass percent looks like. Let's say we have a solution of 30 grams of sodium chloride in 120 grams of water. So that's one way to make a solution. The mass percent, or the percent by mass, is another way to say that, is the grams of solute, so that's 30 grams, divided by the mass of the solution. So what's the mass of the solution? Well, so that's the tricky part about this. The 120 is the mass of water. 150 is the mass of the total solution, because the total solution has water and sodium chloride in it. So the total mass is both of those together. So I'm going to write 120 plus 30, which is the total mass of the solution. So 30 divided by 150 is 1/5, which is 0.2. Or since we usually give that as a percentage, we call that 20% by mass. So we read that as 20% by mass. And it's important to specify it by mass because there are other ways of talking about percentages too. You can have percent mass by volume. You can have percent volume. That's like volume percent or percent by volume is what we measure, for instance, alcohol. Like if you see the little, if you have a bottle that has alcohol in it and it has a little label and it says percent ABV, that stands for alcohol by volume. So it's not the mass of alcohol versus the mass of solution. It's the volume of alcohol versus the volume of solution. So if you look at various household chemicals and things, they are usually given, the percents of active ingredients are usually given in this form, and percent by mass or percent by volume. So you can see how much is there relative to the total. All right. Here's another question using percent by mass. How would you make 50 grams of a 5.0% by mass potassium chloride solution? So we want 50 grams of a 5% solution. How would you make that? In other words, how much KCl and how much water would you need to make that solution? Okay. Yeah.
Moving 50 grams of 5% of KCl. So are you having 50 grams or are you having 5?
50 grams.
You're having 50 grams of something.
Of something, and that something is 5% KCl. So how much KCl would you put in? How much water would you put in to make a 5% solution? That's what it's.
You have 50 grams of something, that's 85%, you have 45% of
No, the total is 50 grams.
right?
5% of that 50 grams is KCl. The rest is water.
Okay.
So how much KCl, how many grams of KCl and how much water? If you go back up, if you look at the equation above, you can solve this by plugging it into the equation and solving for the total of solute, or the grams of solute. So we would go 5% equals the amount of solute, or in this case, KCl, divided by the total mass of solution, which is 50 grams. So what percent of 50 is 5%, or what of 50 is 5%? It's 2.5 grams. So you solve for that, and you find that gives you 2.5 grams of KCl, and then the rest would have to be water. So that would be 47.5 grams of water. And that would give you 50 grams of a 5% solution. So even though we're using masses and we're talking about chemicals and things, this is no different from any other percent type problem. How do you find how much of a certain thing is a certain amount of percent? And that's one thing that makes mass percent nice to work with. It doesn't matter. The fact that it's KCl has nothing to do with it. We're not dealing with moles. We're not dealing with mass, molar masses, whatever. That could be anything, and the answer would be the same. Because we're just dealing with masses. So percent by mass just tells us about what the percents are. All right, let's try another one. Similar question. This is also from the book. How would you make 150 grams of a 40% by mass lithium nitrate solution? Work the same way. How much is 40% of 150? That's another way of saying this. If we've got 150 grams of a 40% by mass, that means 40% of the mass has to be lithium nitrate. So really, this is just saying what percent or what amount of 150 is 40%. What is 40% of 150? That's how you solve this. So what does it come out? 60, right? Yeah. We can set it up like we did in the previous question. If you find it easier, you can also think of this as just 40% of 150, which is 40 or 0.4 times 150 grams. So if 40% is 60, the rest of it is the rest of it. So that means we'd need 60 grams of lithium nitrate and 90 grams of water. So don't get too worried about the specifically chemistry part of this. It's just percentages. It's just a regular percentage, just like if you were, calculating, I don't know, some other percent for some reason. Same thing. Okay. All right, that's percent by mass. The next thing is molarity, but I don't think I want to get into that now because we've only got 10 minutes left. So let's stop there for now and switch to lab. And while everybody's listening, we'll talk about lab, and then we can get started right away when it's lab time.